We've seen that we can calculate an interval that captures the center 95% of a bell-shaped curve using the mean and standard deviation. We can also estimate the center 95% just by looking at a graph of the distribution. In this case, we have a dot plot of annual rainfall in Austin from 1856 to 2012, and this happens to cover 157 rainfall values. So what we want to do is figure out how many dots would be in each tail if we have captured the center 95%. And to do that, we can start by just taking 5% of 157 by doing 0.05, converting 5% to a decimal, and multiplying that by 157. This gets me 7.85, which is very close to 8. This gives us all of the dots in both tails combined. So if we want to split that in half, let's just call it approximately 8 because it's pretty close to 8. We would say that half of them are in each tail, and therefore we would expect to see 4 dots in each tail. Now coming up to our graph, let's count those dots. Starting from the left, we've got 1, 2, 3, 4 before we get to this value right here. And that's going to be between 15 and 20, a little closer to 15. Maybe I'd say 17, or maybe I'd say 16 and a half. Also counting 4 dots from the right gets us to this value here, which looks closer to exactly in the middle. We could call that 52.5. So that I have a lower bound of 17 and an upper bound of 52.5. It would be fine to just call this 52 or 53. We don't have to be super precise when we're showing our work. With Wiley Plus, you might find that you have to be a little bit more precise just because it has a specified tolerance. If you're doing something that's going to be graded by me, if I can understand where your number came from, you don't need to be so concerned about making sure that it's exactly the number that I'm looking for. Keep in mind that we see histograms as often as we see dot plots, and they really do represent the same information. If we wanted to apply this same principle to a graph that was given to us as a histogram, we would want to think of each bar as a stack of dots. So for example, this first bar, it looks like it's of height 1. I'm just going to treat it as if it's 1 dot. And similarly, this bar over here and this one, whereas the next one in looks like it might be about 5 or 6. So we just think of each bar as being a stack of dots. Maybe this one's about 3 dots. When we come into this graph to estimate, we're working with the same data set here. So that was n equals 157. And we're still doing 4 dots, or in this case, since they're not really dots, we have 4 values in each tail. So I would count 1, 2, and then I would see that I'm somewhere in the middle of this bar here centered at 50. Since I'm close to the center of it and it's centered at 50, I'm going to go ahead and accept 50 as my upper bound. Over here I've got 1 and then 2, 3, 4. That gets me right to the edge of this bar. So I'm between 2 bars. I can see that the middle bar here would be centered at 15, so I'm between 15 and 20. Again, I get something around 17, in this case 17.5. So my lower bound would be about 17.5 and my upper bound would be around 50. Note that I just noticed I had these labeled as upper first and lower second. I just swapped them just to make it a little bit more intuitive, so that was a little correction on what I had just done previously. We don't have the exact same values here. The dot plot maybe gave us a little bit more detail than the histogram, and anytime you change the binning on a histogram, you might find that your estimates come out slightly different, but they are fairly close to the estimates that we came up with from the dot plot. So one method of estimating the center 95% is calculating how many observations should be in each tail and counting in from the edges. Another method is to just compare our distribution to about what this bell-shaped curve looks like and train ourselves to get some idea of what that looks like and about how much mass we would expect to see in each tail. So here I would say, okay, this looks approximately like the bell curve. Nice picture. And my center 95%, I would say, appears to go roughly between these two marks that I just drew, trying to draw them in approximately the same position that they look like they are in the graph. So that would go from around 17 to around, I'd go a little higher on this than I got from counting dots, because as we can see, those two last bars are really quite short. So our distribution wasn't quite bell-shaped. But if I just go with this approach, I'm going to say maybe 54 for my upper. So I'll go from a lower bound of 17 to an upper bound of 54. You might find that you prefer one of these methods to the other, but you also would notice that if you don't know the sample size n, you really can't calculate how many observations should be in each tail and count in from the edges, and you really have to be able to just try an approach that's a little bit more like this and wing it, right? So this approach, comparing it to a diagram, is the only thing that works if you don't know how many observations total there are in your graph. If you do know n, then maybe you'll try a combination of the two. Maybe first just eyeball those endpoints, then calculate how many dots or how many observations should be in each tail, and go ahead and count and see if it comes out about right and adjust a little bit if needed. A very common reason for wanting to calculate that center 95% or to estimate that center 95% is to use in estimating standard deviation. If we know that the center 95% covers everything from 2 standard deviations below to 2 standard deviations above the mean, we can then use this interval to estimate the standard deviation. Let's go ahead and take the values that we calculated most recently, which were 17 to 24. I'm sorry, 17 to 54 is what I meant to say. So if I subtract 54 minus 17, I get the length of this interval. That gets me 37. So the length of that interval is 37. Now, if I look at this picture here, I can see that from the lower bound to the upper bound, I cover 1, 2, 3, 4 standard deviations total. So I can calculate that standard deviation from the interval length, (37) divided by 4, and this in this case gets me 6 1/4, 9 1/4. And therefore my estimate of the standard deviation of annual rainfall in Austin over the years we're given is 9.25 inches. Oh, it's funny, this is the same unit as the heights. Wasn't really intended. It's inches of rainfall in this particular case. So we'll see this come up many times, and it's one of the topics from this section that students struggle with the most because there are a lot of concepts behind it. and it's not always obvious from the wording of a question that this is what you're expected to do. But if you're given a graph and you're asked to estimate the standard deviation, or to estimate the standard deviation using the 95% rule, this is the process we're getting at. Come up with your favorite way of finding that upper and lower bound, whether it's by counting dots or just by comparing it to a diagram and getting a really rough estimate, then calculate your interval length and divide it by 4. Another method that you will see sometimes in the videos that the authors of the book do, or perhaps in explanations of the book, is an estimate of x bar and just one of these bounds. If you're using the mean and just one of the bounds, you would find that interval length and divide it by 2 instead. Both methods are perfectly fine, and just depending on the information that you have most readily available to you, one of them might be easier than another. So go ahead and pause the video now and get a little bit of practice yourself estimating standard deviations of these two graphs. I did provide n for you in case you want to try the counting observations method, but it's perfectly okay to just compare it to the diagram and get estimates of about what looks like 5% of the area in both tails. I'll fill these in just a moment. So I just did these by the comparing it to the image method and did a really rough estimate, but let's go ahead and calculate the number of observations that would be in each tail. 5% of 200 is 10. So we would expect to see 5 dots in each tail. Not dots, but values. Counting over here, I can see this looks like about 2, this looks like about 4, so maybe 24 would be a slightly better estimate than 25, since it looks like I didn't get quite all the way through that bar. So I could come back and adjust my values. Over here on the right, I've got 1, 2, and then this bar here looks like it gets me 3, 4, and 5. So maybe I would go with about 75 if I were coming back and adjusting by this method. So anything in this amount of approximate wiggle room would be considered perfectly reasonable for estimating the center 95%. I got a standard deviation of 13. It looks like it would come out only off by about a quarter if I were to try these values instead, since one of them went down by 2, one of them went down by 1, so it's really just 1/4 difference. So maybe we would have gotten 12.75 instead of 13 if we had chosen those values. For n equals 75 over here, we want to calculate 5% of 75. Which is 3.75, which is pretty close to 4. So what we're looking for is approximately 2 values in each tail. And this bar right here is 1. Looking over here at the scale is how we can tell that. This bar right here is another 1, so that 27 looks pretty good. Over here it looks like we had both values in the first bar, so maybe my updated estimate would be 17 as the lower bound instead of 18 as the lower bound, and that would have gotten me a difference of 10 divided by 4, so a standard deviation of 2.5 instead. That actually is a pretty big difference, but still both of these are reasonable estimates. And I just realized why this came out so far off. Of course, I was doing this arithmetic in my head very poorly. That would have been 7/4. This really should have been 2.25. So this is part of the reason we like to do things 2 ways, right? So that we can catch little mistakes like this. So 2.25 versus 2.5, that looks more like the kind of error or variation from one answer to the next that I would expect to see.